Hello everyone. We are going to be presenting a comprehensive study guide on the Mechanics of Materials section of the Fundamentals of Engineering exam by NCEES. Mechanics of Materials is the study of stresses, strains, and deformations as it relates to solid mechanics. Some of the topics that are included under the Mechanics of Materials umbrella that are on the FE exam are shear and moment diagrams, stresses and strains, deformations, combined stresses, principal stresses, and Mohr's circle. At SDSU, the course that covers Mechanics of Materials is CIVI 301. For further assistance with this material, some contacts are Professor Nancy LaCroix, who teaches CIVI 301, as well as Professor Robert Dow, who teaches CIVI 321. For more resources to use when reviewing for the FE, we recommend reviewing and resolving problems that were given in your CIVI 301 and CIVI 321 courses, such as your lecture notes, homework assignments, or even exams. Additionally, the FE handbook may also be a valuable resource to use. Plus, it will help you when you are taking the FE exam, as you will be more familiar with the handbook and better be able to navigate through it in a timed setting. Since the FE practice exam most closely emulates what will be on the actual FE test, we recommend that you practice using the FE practice exam last as a way to best test your knowledge. Considering the importance and depth of this topic, we recommend reviewing and practicing for approximately 5 hours across 4 sessions or days as is displayed in our study schedule here. The first topic that is discussed on the FE for the Mechanics of Materials section is shear and moment diagrams. Therefore, it is our goal to be able to draw accurate shear and moment diagrams for different load scenarios for statically determinate beams. To begin our review, we will first start with the definition of shear and moment diagrams. Shear and moment diagrams are graphs that illustrate the internal shear force and bending moment experienced along the entire span of a loaded beam. Our study plan for this topic consists of 2 steps. 1. To review the key formulas, and 2. Attempt the practice problem. The key formulas that are involved in creating shear and moment diagrams are the equilibrium equations and the definition of a moment as shown. With this review, please take a few moments to solve the practice problem provided. If needed, please take the time to review the solution provided. Otherwise, I will briefly walk through the steps required to successfully solve this problem. Step 1. Solve for the reactions by summing the moments at each support. Step 2. Tally the shear at each point on the beam where the loading changes. Step 3. Using the shear tally, draw the shear diagram. Remember, point loads are displayed as horizontal lines and uniformly distributed loads are shown linearly on shear diagrams. Step 4. Solve for the distance x. Step 5. As defined by the shear diagram, tally the moment experienced at each cut along the beam. Step 6. Using the moment tally, draw the moment diagram. Remember that point loads are displayed linearly and uniformly distributed loads are shown parabolically on moment diagrams.
Another key topic in this section is stresses and strains. The goal is to understand and recognize the different types of stresses and strains and how to use the correct formulas to determine them. Stress is the measure of an applied force acting over the cross-sectional area of the given object. Strain is the ratio between the deformation of an object due to an applied load and its original length. Our plan suggests students review the following definitions and formulas and practice at least 5 problems per week in this area. The following slides provide a summary of all the different types of stresses and strains covered in this subsection of the exam and list their corresponding formulas. Here, axial stress and strain, as well as shear stress and strain, are shown. This slide covers torsional stress and the angle of twist, as well as bending stress. 2 practice problems are provided to demonstrate the type of problems associated with this subsection. The solutions are shown here for students to review after attempting the given practice problems.
One of the most important concepts behind elastic and plastic deformations is being able to read a stress versus strain curve and understand how it predicts the behavior of a material's deformation. There are multiple equations that go along with this subject. For example, the calculations for Young's modulus and torsion. An example problem would be to determine if the stress versus strain curve on the right is for a brittle material or ductile material. The answer is that the material is ductile because we can see that the material yields and remains in its plastic deformation stage for a while before finally reaching its fracture point.
Lastly are combined stresses, principal stresses, and Morse circle. Combined stresses are the sum of all the stresses mentioned in the shear and stress portion of this presentation, including axial, bending, and torsional. Principal stresses are the maximum and minimum normal stress of a particular stress element, and at these stresses, there is no corresponding shear stress. And finally, Morse circle is just a graphical representation of all these stresses and shears that the element will undergo at any given plane orientation. On the left is a drawing of the element. On the right is Morse circle, and we have also included a list of equations on how to calculate principal stresses and any other desired parameter. And listed here is a practice problem with given steps on how to accurately draw Morse circle.